Come all you moonshiners if you want to hear.
Welcome back. Yeah, I'm George. This is really like part two. We did the 120 volt. We're going to now do the 240 volt PID. And you're going to be surprised at how similar, almost identical it is to 120 volts. Now, there can be some variations, and we'll discuss those. It's real simple. Now, if you're not comfortable, this is sort of like the disclaimer. If you're not comfortable with electricity, and I know a lot of people are not, then I understand. Pass it off to someone else. But if you follow these simple, basic rules, you'll be just fine. But it's totally up to you. I encourage you to at least watch it and see what you think. Okay, look, when you're working with 120 volts versus 240 volts, you're really working with, I like to say, kind of like the same thing. It's exactly the same, only different. Does that make sense? No, of course not. Yeah, but it is. It's exactly the same, only different. Here's the major difference, okay? First of all, always make sure that your wire is rated for the amperage. Remember what we said? We said voltage is the sort of like the horsepower, the oomph, and your amperage is the flow, the push. I just read a message back on the other video, and it's one guy reminded me that I used it before, said it's like in a water hose. The water is the voltage. The pressure in which the water flows through the hose is sort of like synonymous with the amperage. That's kind of what we're talking about. All right, so you get this, or you got that. Make sure that your conductors, your wires, are rated for what you're using, okay? Up to 20 amps. We're going to use 12 gauge wire. It's standard, kind of like household wiring, except for some of your off the shoots that might go to just lighting alone. That may be 14 gauge. Switching in a lot of cases could be 14 gauge. It all depends on where you are in the country. Oh God, I'm getting off on a tangent. There are different plugs for everything, of course, because your plugs have to match the rating of your wire. So if you can use, I don't have a regular plug out here. Yes, I do. This is a 240 volt 20 watt or 20 amp plug, and you'll notice the difference because they make these where one of the blades is sideways, and the reason they make it like that is so you can't accidentally plug this into a 120 or vice versa, a 240 into a 120, because the blades won't fit into the receptacle. It just kind of makes sense. So that's the standard one. That's kind of like what most of us would use, because this is good for up to like a 3500 or even a 4000 watt element. That's really, you can, and formula. What's the real quick formula? Okay, is power divided by voltage. Let's say, as an example, we have power divided by voltage, E, electromotive force. Power divided by voltage. Let's say we have a 3500 watt element, all right, just for the sake of argument. 3500, and we're going to run that on 240 volts. So 3500 divided by 240 means that at max draw, we're going to draw, this says 14.58, so what's that? Yeah, 14.6, or you can just round that off to 15 amps. So therefore, yeah, one of these plugs would be perfectly okay because it's rated at 20 amps. You follow? Let's say, for instance, this was a 5500. A 5500 divided by 240 will draw, I got to erase that for you real quick, 22.9 amps or 30 amps. So you're going to draw 30 amps at 100%. If it's operating at 100%. So therefore, in that case, this plug wouldn't work. You'd need to step up to this plug. This may be familiar. This is what's on your dryer in most cases. Most dryers require a 30 amp run. And you'll notice that if you open up the box and look inside, it's got 10 gauge wire to carry that 30 amp potential. All right. Now, some of you may have one of these. This is one of those locked, and it's the same thing. But it's rated at 30 amps, and that's because the oomph of the receptacle or the plug matches the wire gauge size, which is matched to the potential amperage you're going to draw. We got all that? Pow. All right, let's get this out of the way. I know someone's going to ask out there, well, George, what about the 4-wire? We're going to talk about that, but it'll only be briefly because that's all it requires. We've got, here we go again, we've got green, black, and blue. We're going to use blue to represent white because the convention is in a 240 volt circuit, 20 amps or lower, or 30 amps really. No, 20 amps or lower. You're going to run, it's going to be standard wire. It's going to run the same as everything else with the exception of the plug and the receptacle. So you've got this plug, all right, and you've got 120 volts. This represents the white wire. 120 volts. And lo and behold, yes, you're going to have the green, which is the ground. And where's that green go? It goes to the chassis of your device. All right? Outside of your still, on the side of your bake oven, whatever device you have on the far end that you're going to be controlling or working with. Now, some smart guy out there now has already figured out, he's going to say, well, George, where's the neutral wire? Well, in 240 volt circuit, the 120 volts and the 120 volts are 180 degrees out of phase, which means when one is high, the other one is low. And then they cross. And that sine wave, you're familiar with sine waves. Well, the sine wave of a 240 volt circuit is opposite each other. So they continue to continuously cross. And what that creates is its own neutral. So you don't require, there's no neutral required. Here's how this works. This is the beauty behind this. So if you're going to wire a 240 volt PID because the PID can handle it, the solid state relay doesn't really care. Your heating element is already rated at 240 because it's above a 2,000 watt element. And it'll be written right on the bottom of it. It'll tell you right there if it's 240 volt or 120 volt. So all of this is already in line. Your volt amp meter, your transformer, and of course the fan doesn't care because it's only going to get 5 volts from the transformer. So all of that works. Here's what we do. What was the first thing we did with 120 volt? Yeah, we ran our, well, let me get the blue one here. Yeah, we run one lead, runs directly to one screw, doesn't matter which one it is, on your element, because the element doesn't care which direction that's going to flow. It runs to one. The other lead, which is another 120 volts, which is out of phase of this one, we're going to run that to pin number 1 on the solid state relay, because the solid state relay is now our switch. You see, it's a broken contact. And then we're going to run another wire from pin 2 to the heating element. That's it. Now you've got your complete circuit, so you add 120 and 120 together, you have 240 volts. That's the only difference between a 120 volt circuit and a 240 volt circuit. The second line in a 120 volt circuit, this is a neutral. And it's a current carrying conductor, but it's a neutral, which means it doesn't provide any power. In a 240 volt circuit, they each carry 120 volts, but they're out of phase of each other. And together, these two together equal 240 volts. So if you follow, if you follow the wiring diagram for the 120 volt wiring, and you're using 240 volts, you'll find out that they will be duplicate of each other. They both look exactly alike. So isn't that interesting? The only difference is you're running 240 volts as opposed to 120 volts. Gosh, I can't say that enough, can I? Now here's some key points of interest to think about. Yeah, when you do connect your volt amp meter, and I'll point you back to that video. That's the one right before this one is wiring that, because we go through every. Let's do it real quick. Oh my goodness, yeah. Now all we've got to do now is we've got to connect pin number 6 with a small gauge wire, pins number 8 to 3 with a small gauge wire, because that's our signal from the PID to the solid state relay. We've got our thermocouple out here. We've got a positive. We've got a negative. And what happens if you hook those up backwards? Will it work? Yeah, it'll work, but when you hold the thermocouple and you know it's supposed to be getting warmer, the temperature's going down. You'll notice that the numbers are going, they keep precipitously going down. You go, oh, I got that hook. Switch those wires around, and when you hold it, they'll start reading up. So it'll read backwards if you hook these up backwards. Okay, let's connect our PID. PID works off of 240 volts. We run a wire from here to pin number 9. I can do it a whole bunch of different ways. I do it from here because it's a whole lot easier to see. I probably go from there, but I can go from here, I can go anywhere. But if I tap off of that other 120 volt line, go to pin number 10, I now have my PIDs powered. So when I plug it in, my PID comes on, it starts to read the temperature. If the temperature is not where it is set for, if it's below that, it sends a signal through pins 6 and 8, activates my solid state relay, makes the connection, bam, we have action. So now that works. So the heating element comes on. When it achieves its temperature or its set, it discontinues sending the signal, opens up the circuit, and then the element goes off. So see, it works exactly the same way, and we can do the same thing for adding the volt amp meter, which is an interesting point here. Volt amp meter. All we need is a hot. Oh, and I should have done this. You know what I mean. I want to jump those. There we go. And all we need then is also our second hot. And what do we call that? The small sensor. A lot of people would think that you put it around both wires, but if you do that, it's like doing it with on 120. It'll cancel itself out. Because an amp meter, this sensor senses the magnetic field that's created by the flow of electricity, the amperage, the flow in the conductor. And if you put them side by side and put that donut around both of them, when one's hot, the other's not. And so what will happen is it'll cancel itself out. You'll get a weird reading or no reading. So you put it around one. Put that donut there. Connect your red, the positive and the negative. And now you have that connected. You see, it's the same system, it's the same mechanism for adding components. And you would add your fan in the same manner. You could tap right off of the volt amp meter and run the fan. You could tap off of pins 9 and 10 and run the fan. Now, someone out there is going to ask the bright question about a 4-wire. Well, if you're going to run 4 wires, what is that? What does that entail? Let me show you. Isn't that amazing? All right, now 4-wire. What do we have when we have a 4-wire hookup? What we actually have, and you may recognize this in some of your major appliances. Some stoves have a 4-wire hookup. Now there are some washer-dryer combos that have this as well. And the reason for sometimes a 4-wire hookup is because you have a part of your system that requires 240 volts and another part of your system that requires 120 volts. And you don't have the luxury of dual voltage items. This may be the case, something you wind up with. You may wind up purchasing, go on Amazon and you get the volt amp meter, and it won't withstand the 240 volts, it's only rated up to 120 volts, so you can't use 240 on it, you can only use 120. So what do you do? So an average layman would think, well, why don't I just hook a 120 volt leg and then use the ground? And that's that's a big no-no. Never, ever, ever use a ground line as a current carrying conductor. That is there for your safety and your safety only, and the safety of the system. Just in case, in the event that you have a short circuit or somehow it fails and it short circuits to your system, it doesn't electrify your element, or it doesn't electrify your system itself. What it does is it faults to ground, and in most cases it will blow a fuse. So that's what that is for. So never, ever, ever use a ground ground line as a current carrying conductor. You never want electricity to run through that. Okay, you may be familiar with this. Plug may look like that. And it's got 4 holes in it. And this one down here may even look like this. That's just another style. That's all that is. It's just to ensure that there's only one plug that'll fit that. And this is what we could normally refer to as a 4-wire system. Well, actually, we call it 3-wire because everybody considers ground to be natural. It's normally there. So here's our ground wire. And where does that go? That goes here. All right. Now, in this particular case, if you're going to use this system, what could you potentially do? White. The blue is the white. This one is going to be your neutral. And your 2 blades all opposing each other are almost in every case, if you're going to purchase it, in almost in every case, they're going to be 120 volts. And guess what? 120 volts. So what this gives you, it gives you the ability to use these 2 for 240 volts. Plain and flat out, all you got is 240 volts because it creates its own neutral. Or you could wire to one of these and this neutral, and now you have a safe 120 volt circuit. I'll show you how that works. When we do that, we normally use a distribution block. A distribution block, again, these are available on Amazon too. They're about $8 for 2 of them. And this one's rated at 25 amps. I've got one here that's rated at 45 amps, and you'll notice that it's just beefier, bulkier, because the metal has to be able to conduct that high amperage. Now what these come with is you can use a single block and then block off 2 sides. What I mean by that is they come with these shunts. You'll take a shunt, and I've got 1, 2, 3, 4, 5, 6, 7, 8. So I'll cut off 4 of these, and I'll place these on these 4 screws. And what that shunt does, I get a screwdriver. What this shunt does is it connects all 4 of these screws together so that power going to any one goes to all 4 of these. Now, what's neat about this is on the other side, you can cut off the other 4, and they come color coded, so you can use the red ones, and that would be natural or normal. Now, you have 120 volts on these first 4 pins, screws coming out here, coming out the top, and you've got 120 volts going on these 4 screws coming out the top. But they're out of phase, so that means when you use one of each of these 4 pairs, you've got 240 volts. Oh, beauty, beauty, beauty. Let's draw one of those. One, 2, 3, 4, 5, 6, 7, 8. And what I'll do is I connect these 4 together, and then I connect these 4 together. So far, so good. This is cool. I'll run one wire to here. You know, I should have put this on this side because it would make a whole lot better sense. But does it really matter? Nah. And you'll see why in just a second. So I'll run one wire to here, and that means that all of these screws are from 120 volts. I'll run my second wire to here. Now all of these screws are 120 volts, but they're from 2 different phases. So if I run, watch this. This is what gets good. I run, nothing changes now. Nothing changes. So I got 120 volts. This is going to be a 240 volt, 5,500 watt element. And I'll run this one to here. So now I've got power for my element. Now I need power for my PID. I can use low voltage wire or low amperage wire, you know, 16, 18, 20 gauge wire, because it only draws 5 amps. And I can run that little tiny wire like this to here. I can run another little tiny wire from here to there. You see what that does? That distribution block gives me a place to come from. That's all it does. It just gives you a place to tap from. I've got everything going in on this side. I can just tap from any of these screws on that side. I can actually tap 2 from one screw if I wanted to, but I've got all these extra screws left over. Let's say, for instance, let's do this. Of course, we got to connect pin 6. We've got to connect pin 8. That's to make that work. Then we've got to have our thermocouple, and we got a hot and a ground. So far, so good. So we've got everything. Everything is exactly the same. Now, where can you put it? You could put a switch anywhere you want. You would normally put a switch here. You could. Where's another place that there is a switch available? If you're close enough to it, your main circuit breaker. You just go to the main circuit breaker and turn that off. And that takes all the power out completely. So let's put this back on. So we're not going to concern ourselves with a switch at this point. Now, what if we hook up the volt amp meter? Of course, we've got our donut. We could put the donut on this line or that line. It doesn't matter. Just don't put it on both lines together. It's just one or the other. And I'll run the positive and the negative. And what do? We take one line from the red side, 120 volts, and one line from outside, 120 volts. Now, what if by chance we have a volt amp meter that will not withstand 240 volts? Well, simple. We just run an additional wire from the neutral and then run either one from the black or one from the red. It doesn't matter. And now you've got 120 volts isolated. It's an isolated 120 volt circuit. Oh, you could have done the same thing for the PID if you want to run it off of 120 volts. You could have isolated. You could have done that as well. And you can do the same thing with the fan. So you have all of those options. Now, where this really comes in handy, this distribution block, is where you have, let's say for instance, you have multiple elements. Yeah, let's say we've got more than one element. We've got 2 elements. Well, if you have two elements, and this is where you will probably require to have a 50 amp circuit with a 50 amp plug and a minimum of 10 gauge wire because of the amperage draw through that system, right? Now, in this particular case, what we're going to do is we're going to run another wire because we want both those elements to work. We're going to tap here, and we're going to tap here. So this way, when your solid state relay is activated and it completes that circuit, it turns on not only the top element but the bottom element, and the top element and bottom element are already connected to the other 120 volts, so you wind up with 240 volts going through both elements. It doesn't get any simpler than that, and I'm sorry to put it that way, but that is the nature of the beast. We have one other issue, or one other small item to consider, because somebody out there is going to say, well, George, if I have 20 amps running through this line to operate those elements, and so that means I'm drawing 20 amps from here and 20 amps from over here, what about this small wire? Isn't that 20 amps as well? You said I could use a small wire, a low amperage wire. Well, yeah, absolutely. Just because 20 amps is running through this line, this large line, your major amp carrying conductor, doesn't necessarily mean that that's what's going through this line as well. Remember, I said this earlier in the other video too, is that the amperage through the line, the flow of that electricity, is only going to match the draw of the device. So if this PID only requires 0.5 amps to operate, it's only going to draw 5 amps. Even though there's 20 amps available, only 0.5 amps is going to go to it. If by chance, on this line, if it only requires 10 amps, it's only going to draw 10 amps. If it requires the full 20 amps, it'll draw the full 20 amps. If it draws 22 amps, it'll take 22 amps. But just because you have it available does not mean that that's what's actually going to flow. So you got to think about it a little bit. It's not like just turning on the spigot and you're going to turn on 20 amps worth of power and see what happens. Your power flow will always equal what the requirement is of the device. The device will control that. How's that? That make better sense? Yeah. But that's it in a nutshell. So we've wired 120 volt. We've wired the 240 volt 2-wire or 3-wire, however you want to describe it. And we've wired the 4-wire or 3-wire, however you want to describe it. Remember, because the ground is a given. So we have two 120s and a neutral, or we have just two 120s and a ground. We can wire it either way. But we use a distribution block in this case to get it where we need it. And that way we don't have to splice in anything. Could you have wired this without a distribution block? Yes. Yes, there are methods for doing that too, and it's called splicing. Yeah, you can splice wires together. Again, I want to reiterate that there are multiple ways of wiring this. This is probably the most direct method. Always start from your end, your requirement, and work all the way back to your source and start adding your components where they fit in. And make it simple on yourself. Draw your diagram out, and then when you start to wire it, follow it. It doesn't have to look like this in the box. It can be rearranged any way you want in the box as long as the wires go there. You know? Doesn't really matter. I hope we've answered all your questions. You have a safe time and a fun time doing this. Here, hey, one hint is if you hook up something like this, if you hook up one of them wrong, something's going to smoke, something's going to buzz, something's going to sizzle, something's going to spark. Unplug it. Turn it off. Go back in and look at it again. Hope you didn't burn something up. But chances are you're not going to hurt anybody. Keep your fingers out of it. And happy distilling.